Cool, so let's get started. All right, so for this lab, we are going to be going over collision resolution methods, continuing from last week's lab of hash tables. Okay, so as I'm sure you are all aware, midterm results are out. Regrade requests should be open now for the pre-response. And we aren't going to make the answers to the multiple choice visible because we don't want people to be like collecting the answers and releasing them for future semesters, because we do intend to reuse some of them for next semester, because next semester is probably going to be remote also. But yeah, if you want to get the answers for a multiple choice or have any questions about them, feel free to come to office hours when it's not too busy. So preferably after Project 3 deadline has passed. And then, well, I will be happy to answer your questions about those. So recall that Project 3 is due on November 12th. So you have like 10 days left. Yeah, this project is definitely a lot more heavy on the planning side. So I recommend doing a pretty thorough like planning before you actually start coding anything. And so this Friday, Lab 6 is going to be due. Lab 6, remember, is just the survey that if over 75% of the class takes the survey, then everyone gets points for it. And Lab 7 is going to be due next Friday. Any questions about that? Okay. And if you have any questions during this lab, again, feel free to type it in the chat or just interrupt me, because there are, like, besides me, there's like 11 people in this. Okay, so there's our agenda for today. Okay, so let's talk about hash functions. So if you recall from last week, a hash table is basically what the unordered map and unordered set represents in C++. It's an abstract data type that allows for O of 1, so constant time insert, lookup, and deletion of an element. And it uses a hash function to map keys to the hash value. So basically, like visualizing it, you like have a key here, and then like you compute some sort of function to figure out where in the hash table to put it. So it's a way to map from a key to the index of the hash table. So hash functions. We want you to use modulo to keep the index, the output of the hash function, within the limits of the size of the table. So yeah, because you have a limited amount of space in memory, but we also, the output of the hash function might be too big. And so you can just modulo the hash of the key by the number of buckets that you have, and that'll give you something that'll fit inside your hash table. Any questions about that? All right. Okay, so there are two invariants, so things that are always true about hash functions. Hash functions will be consistent. If the two keys are equal, then they must always hash to the same thing. Otherwise, it'll be non-deterministic, and you'll be looking at different places if you try to find them in the hash table. So yeah, anything, the input will always map to, same inputs will always map to the same output. And also hash functions are efficient because all hash functions should be computable in O of 1 time. Because otherwise, if it's slow, it's not O of 1 time, then the purpose of using a hash table is defeated. So we want, hash tables are all about fast lookup. Okay, so looking at these, oh, I guess I deleted that. Oops. Anyways, so there's the answer there, but oh, okay. So out of these three hash functions, all of them have an issue, and that is that there's a lot of collisions. So even if keys are different, there's a high probability that, well, there's going to be more collisions than we want. So for example, in hash 1, this will always return the index 1. So there's basically no uniqueness in like the hash. It's always going to map to the same thing, and then you're going to have collisions in terms of where you want to put your key in the hash table. Hash 2 basically either returns 0 if it's empty, or returns like the index, I guess, of the first letter in the alphabet. So it takes the first letter and subtracts the capital A from it. And hash 3, what that does is it takes the first letter, all the letters of the word, and multiplies it by the index of that letter and 100 and sums it all together and then returns the result. But even with that, that's not necessarily a good hash function because there still could be collisions. Like if you had, for example, like oops and like soup, so any like anagrams of each other, that'll end up in a collision. And then we get sad. Okay. So let's do an exercise. Okay, so what does this hash function do for the following keys? So what would the output of the hash function be for zebra? Can anyone tell me? 26. Remember that we are zero-based index. 25. Yeah, it would be 26 if A was 1, but A in this case is 0, because like A minus A is 0 in CS land. So this will end up being 25. What'll a dog be? Anyone? 3. Yeah. So dog will be 3. And then what'll F be? Or fest? 5. Yeah. Okay. So that's what the hash, that's what hash 2 will return for each of these keys. Before I move on, does anyone have any questions about that? Yeah, just a relatively simple hash function. Okay. So what bucket would the following keys be inserted at? And so the difference between bucket here would be if, for example, well, let me actually rewrite what we said the hashes were. So 25, 3, and 5. And basically, the bucket is going to be where we would actually put it in our hash table. And we know the size of our hash table is n. So if we had like n, pretend there's like 10 rectangles here. I don't want to actually count. But we're deciding which like place in the hash table we would be inserting our keys. And as we said before, we want you to use modulo here. So the bucket for 0, let's actually do dog first. So the bucket for dog would be 3 modulo 10, which would just equal 3. And so we put dog at 0, 1, 2, 3. Yeah. And so what would the bucket be for zebra? 5. Yeah. And for fest, also 5. Okay. So there's an issue here, and that is that zebra and fest map to the same bucket. So we need to have some way to address that. So we have a hash collision here. So the way that we would deal with hash collisions is using some sort of collision resolution technique. Okay, so you would need to resolve the collision. So let's talk about how we resolve collisions. So there's two techniques that we go over in this class for collision resolution, just like general techniques that are commonly used. So the first is separate chaining, which is storing all the colliding key value pairs in the same bucket, but in a linked list for that bucket. So the key here is a linked list. So I'm not a huge fan of this picture, but basically if you had like a few keys, like let's call this key 1, key 2, and you had several, let's see, you had like several items that hashed to key 1, you would put the first item there, then you'd add the second item, link to the first item, and then keep on going. And so it's just a list growing from that key. And same for key 2. Yeah. And so for open addressing, you would be storing colliding key value pairs in another bucket or location. So every bucket / location would either be empty or have a value in it. So there are different ways to implement open addressing, which we will go over in just a sec. Okay, but before that we do that, let's talk more about separate chaining. So again, chaining uses linked lists to allow buckets to hold multiple elements. And whenever there's a collision, the new element is added to the bucket's linked list. So can anyone tell me, since we're working with linked lists, what would the best case, average case, and worst case of insert or lookup be if we were using separate chaining? So let's talk about best case first. What would the best case be? O of 1. Yes, exactly. So for O of 1, our best case is O of 1, and that would be if there were no collisions. So just a ideal hash table, O of 1 lookup, super fast lookup. What would the average case be? Okay, Jonathan says O of n. Does everyone agree with that, or are there any other answers? O of n over m. And would m be like the number of like buckets? Okay, I see. So the answer here is actually O of 1. And the reason for that is like, so it's like an average case, right? In the average case, you would have ideally a lot of buckets. So yeah, kind of like amortized O of 1. So Jonathan's kind of got it. So like, you would have a lot of buckets, and so in the average case, you wouldn't have a collision. Like everything would just hash to a new index. So average case is like few collisions, like and even if there were a collision, ideally you would only have like one value already in the linked list, and so you just like append to the end of the linked list, which would be like one element lon, and so when you add to the end of it, because it's one element lon, it's still O of 1. Does that make sense? Okay. So what would the worst case be? O of n. Yes. So worst case is O of n because it's kind of intuitive what the worst case would be, but it would just be like everything hashes to the same bucket. Which is not good. Basically, you're just putting everything in a linked list at that point. Okay, any questions on this slide before we moved on? Okay. So let's talk about open addressing. So for linear probing, again, open addressing is where everything goes to its own bucket. But let's call k the key and h of k to be the hash value, where h is the hash function. And linear probing is when the interval between probes is fixed. So the step size between probes is 1. So basically, you would try to put something in h of k in the default like hash function output. And if that bucket is already occupied, you would try the next one. And if that one's already occupied, you would try the next one, and so on and so forth until you find an empty bucket. And also you would wrap around if needed, which is like basically just moduloing the output of the hash at that point. And so the formula here is just h of k, so the hash value, plus I, which is like the linear probe, like the number of the linear probe that you're on. So the 0, like if I is equal to 0, then you're not doing a linear probe yet. If I is equal to 1, then you're doing your first linear probe, and so on. And then modulo n, which is the size of the hash table, or the number of buckets that you have. I think it's a better way to phrase it. Oh, that literally is right there. Well, anyways. Okay, anyone have questions about this slide before we move on to a linear probing exercise? Okay. So let's try to do our own linear probing. So let's say that we have a 6 buckets and this hash function, which is like the bad one that we talked about earlier, but just for the simplicity of this example, let's pretend that it's good, or it actually is bad because we want as many collisions as possible because we want to practice linear probing. So what would the output of hash 2 be for each of these? And what bucket would each of these go in? So can you give it to me in like a list, or like the bucket, comma, bucket 2, comma, bucket 3, comma, bucket 4? Actually, let's do, just tell me the hash values first. So what's the formula again? Okay, so the formula is here. So hash function plus I modulo n, but let's start simple. So like so what would each of these hash to, first of all? Like just hash to, like without doing any of the probing yet. So cat would go to 2 because it's the third letter in the alphabet. Cop would go to 2 as well. And C, then cartographer would also go to 2, right? And D, yeah, here we go to 4. Okay, so that's the output of hash 2 for each of these. So, okay, let's start putting these into our hash table. So we can simply say that cat would go into 2, right? Because there's no collisions yet. It's we start off with an empty hash table. So cat would go to 2. Cop would first we'd look at 2 and see that it's full. So we look to the next one. This would be 2 plus 1, because it's like the h k plus I thing that we were doing, right? And then modulo 6, because we have 6 buckets. And then we put cop here. And then ear would go into 4 because it's empty. And so we can just put it there without doing any linear probing. And then cartographer would go, first we look at 2 again and know that it's empty. I'm gonna do a different color. That's full, sorry. So we go to 3, that's full, go to 4, that's full, then go to 5, and finally that's empty, so we put cartographer there. And I do not like that they picked such a long word, but whatever. Okay. Oh my gosh, it fit. Okay. All right, any questions about how that worked? Cool, doesn't seem like it. Yeah, so linear probing just literally just looking like linearly, like traversing the table linearly until you find an empty spot to put the key in. Okay, so now your turn. If you want to insert duck into the hash table, where does it end up? 0. Yeah. Yeah, so duck would, first of all, hash 2 would become, hash 2 of duck is going to be 3, right? And then if you wanted to, I'm going to write out this. So 3 plus 0 modulo 6 equals 3, but that's full. So we don't want to, we want to look into the next one. 3 plus 1 modulo 6 equals 4, but that's also full. So we look to the next one. 3 plus 2 modulo 6 equals 5. That's full. So we look to the next one. 3 plus 3 modulo 6 equals 0. So now that's empty. And we can put duck in space 0. Yeah, because of it being 6 modulo 6. Exactly. And the reason, like, this may seem kind of like redundant how I'm like writing all this stuff out, but it'll be helpful for lab 7 because you are going to be implementing your own like hash table like under the hood linear collision resolution stuff. Okay, so quadratic probing is going to be basically the same idea as linear probing, where you're going to keep on looking until you find the next empty spot. But you're going to be, instead of incrementing 1 by 1, you're just incrementing first with quadratically. So like 1 squared, and then you'll look to the next ones, like 2 squared. Then you'll look at, oh, what happened? What? Okay, so you'll be looking at 3 squared, and then 4 squared, and so on. And of course, wrapping around as if needed with the modulo n. So the formula is, again, the hash function plus the collision number squared modulo n. Okay, does that make sense? Any questions? Okay, if not, let's move on to another example. So this time we have n equals 10 buckets. Our hash function is the same as for linear probing in our linear probing example. And we want to insert the same 4 items in order with the same hash values. So let's start off with cat. So cat is going to end up at 2, right? Because 2 is already empty. Cop is going to end up where? 3. Exactly. Yeah, because we have 2 plus 1 squared modulo 10 equals 3. So cop goes there. Where is ear going to end up? 4, because 4 is already empty, so we don't really need to do any further probing than that. Where's cartographer going to end up? 6, exactly. So that's because 2, so we're going to look at 2, 2's, we're going to look at 2, 2 is empty, or sorry, full, so we can't put cartographer there. So we'll look to 2 plus 1 squared. Let's do this. But that's also full. So now we'll be looking at 2 plus 2 squared. So that'll be at 6. And we can safely put cartographer there because 6 is empty. Oh, sad, didn't fit. Okay. Cool. Any questions about that? Is there an advantage to quadratic probing? Good question. So the motivation behind using quadratic probing over linear probing is to, I guess, minimize the amount of probes that you do. If, like, for example, like what if everything mapped to 2? Then instead of having to check, like, keep on going until you find an empty space with linear probing, assuming that everything like is clustered into one area in the table, then quadratic probing just assumes that since that, like, the more probes you do and the more like unsuccessful probes that you do, then you'll want to look even further than usual. So like if you look one past the place that's full and that's full also, then you can like assume that, oh, because of that, like this area is like just all empty. And then you'll keep on looking like further than just like looking one past. Like if you're sitting, like if you're trying to find a seat somewhere, uh if like there's like a row of people of seats that are occupied, like what I do, and I'm sure like a lot of people do, it just like instead of looking towards the end of the line, they're like, okay, I'll just look like somewhere else then. That was kind of a long-winded explanation, but that's kind of the idea behind quadratic probing. Yeah. Okay. So let's do duck again. Oh, that's the answers. Okay. So let's do duck again. Where would that end up? I know there's a few steps to this, so you can take your time. Okay. So 8, but I'm not sure. 7? Yes. 7 is where it should end up. But yeah, quadratic probing, like it's like the concept seems like, oh, okay, like it's quadratic. You're just doing the same thing as linear probing, but you're squaring stuff. But remember that you're adding it to the hash. So if you had 3 as the hash, that's full. So you would look to the next one. And so I equals 1 here. That's the ith collision. But you'd be doing 3 plus 1 squared modulo 10 equals 4. And 4 is also full. So you'd be looking to the next one. Now you've had 2 collisions. And so you do 3 plus 2 squared modulo 10, which is now 7 modulo 10, which is 7. And so you would look there, and that is empty. Yes. You always reset the collision count. I think you have the right idea. But yeah, you're always like adding to the collision account once you like keep on colliding. Oh, I guess like with every new key insertion, you would be resetting the collision count back to 0 because you haven't had any collisions with that specific key yet. So that goes at 7. Okay, any questions about this before we move on? I equals 3. Oh yeah. Yeah, you'd be resetting. Yeah, I equals 0 for each new key insertion. Yeah. Okay. All right. Oh. Okay. So now there's another form of open addressing which is called double hashing. And double hashing basically means that you have 2 hash functions that you'll be using. So HK in this explanation is going to be the first hash value, and F of K is going to be the second hash value. And so interval probes are going to be computed by using the other hash function. So you would start off with HK plus 0 because you've had 0 collisions. F of K, so that's just HK. And then you'd move on to H of K plus 1 F of K because you had 1 collision. H of K plus 2 F of K because you have 2 collisions. And then so on and so forth. And then so the function for this collision resolution method is going to be H of K plus I times F of K modulo N. Any questions about that? Okay, if not, let's see this in action. So I like how it says quadratic probing, but it's very much not quadratic probing anymore. Okay, so if we inserted these 4 items in this order, so cat, then cop, then ear, then choreographer, where do the keys end up? So let's start off with cat. So we know that, well, actually, tell me, where would cat go? So where should we put cat? Spoiler, it's the same as before. The hashes are already on the screen. They are already on the screen. But I guess we'll see in a moment. So, okay, cat would go at 2. Cop would go at 2. But, okay, so cop would collide with cat, right? Oh, cop would collide with cat. So after that collision, where would cop go? Cop go at 7? Yes. So cop would go at 7 because we'd start off with 2, and then it would collide with cat. So now we have 1 collision. So we do one collision times the second hash, which is 15. And then we modulo that by the number of buckets, which is 10. And so it would be 17 modulo 10, which is 7. And so cop would go at 7. Okay. So where would ear go then? Four. Yeah, because there are no collisions and the 4 is empty. Where would cartographer go? 9. Yes. So yeah, cartographer would go, well, first you tried to, but that's already been taken by the cat. So you would do 2 plus 1 times 17, modulo 10, which is 9, and so you just put cartographer there. Good. And so, yeah. Okay, any questions about that? What would you do with car? Yeah, so car would, let's see, so the hash for car would be 2, hash 2 would be S back minus A, R, so it's 17. Okay, so you would do 2, yeah, so you would try 2 plus 17, but that wouldn't work because it's already been occupied by cartographer. So you would try 2 plus 2 times 17, which is 6, I believe. Like 34 plus 2 is 36, modulo 10 equals 6. And so you put car there. Yeah, I'm pretty sure it's it. Is that too fast? Did that make sense? Okay, cool. So how would you handle deleted elements? So, okay, assume that we inserted cat already into bucket 2, and then inserted cop into bucket 3 after a collision. And okay, so what if we tried to find cop after removing cat? So what if cat were all gone? And ooh, I wonder if I can. Wow, I love no apps. Okay, so now cat is gone. And if we wanted to insert or wanted to find cop to see if it's in our table, we would look at 2 and be like, oh, that's empty. So cop doesn't exist in the table, right? That's not true. Cop does exist in the table, but we deleted cat. So the solution to that would be to have some sort of way to mark that a cell used to have something, but that was deleted. So we would call it like deleted, or like have some other way to mark that. Yeah, so it looks empty. So we put deleted there. Any questions about that before I move on to an example, I believe? Yeah. Oh my God, am I so Cassie? Okay. Let's move on to the linear probing erasing exercise. Okay, so let's erase cat and replace it with a deleted marker. Let's erase cartographer and replace that with the deleted marker as well. So now we want to insert cartographer. And the way that we would do that is to, so we would look to see if cartographer already exists. So we'd look at 2, and we know that something was deleted there. So we would look at 3, that's actually full. So we look at 4, that's actually full. with the cat 5, something was deleted there, and we still haven't found cartographer yet. So we would look at 6, and that is actually empty. And so we know that cartographer does not exist in the table. And so we would insert cartographer there. Does that make sense? What I did there? So I think it has a, yeah. So cat would be erased. And cartographer is erased. And then we need to insert cartographer. Oh, sorry. I messed up. We know that cartographer doesn't exist in the table, so we wouldn't insert at 6 actually. We'd insert it at 2 because 2 is actually empty. So yeah, sorry about that. Okay, does that make sense? So we can just insert the original hash value. Yeah, so the purpose of like having the deleted element is to make sure that in the table, cartographer doesn't already actually exist. So you would like keep on looking until you find an empty spot in the table, or until you find the value cartographer. But otherwise, if cartographer doesn't exist in the table, then we'd put it at the earliest like empty cell, which would be at hash 2, because it was technically empty. Okay. So I think that I can move on unless anyone else has any questions. Okay. So let's talk about the performance of hash tables and something called the load factor. So with linear probing, we entered these 4 words and obtained these buckets. So there were several collisions. And so, okay, we had cop collide with cat, so we had to put it at 3. Cartographer collided with cop and ear, or sorry, cat, cop, and ear, and so we had to put it into 5. So what does this show about the performance of our hash table as it gets filled up? It becomes worse and inefficient. So the reason why it became worse was because there was a lot of, like, our hash table was getting filled up, and there were less open spaces, basically. And that's where the load factor comes into play. So we call the load factor, we call the ratio of the number of elements in the hash table divided by the number of available buckets, like the size of the hash table, the load factor of the hash table. And that's a key metric for measuring the hash table's performance. So the higher the load factor is, the more likely you are to have a collision. So to increase the performance of the hash table / reduce collisions, you can use prime numbers to for the size of the table, because fancy math stuff of basically if you have big numbers that are multiples of each other, and you try to modulo it by the table size, they will often collide with each other because they have a factor in common with the table size. So having a prime number be the table size minimizes that risk. You can use a good hash function that avoids collisions, and the key thing, you can keep the load factor low. Less than 0.75 is like kind of like the bare minimum, but some would argue that like having it as less than 0.5 or even less than 0.3 is better, but that takes up more memory. You can pick whichever one for lab 7. I think that it won't be too bad in terms of like memory inefficiencies. Yeah. Any questions about load factor before we move on? Oh, also another thing, this like how to increase performance / reduce hash collisions is sometimes asked like on the final. So maybe remember this. Okay. So the time complexity of hash tables are on average O of 1 plus K of n, K over n, which if n is a lot bigger than K, then it would just be O of 1. But K over n is basically the load factor, where K is the number of keys and n is the table size, and O of 1 for computing the actual hash. Okay, and also worst case, it would be O of K. And like similar to the linked list like idea from before, that's basically just searching through all of your elements until you find the key that you're looking for. Okay. Yeah, so, and then space complexity, oh, sorry. So important concept that someone said before, but amortized if rehashing / resizing is done, similar to a vector's amortization. And basically, since you want to keep the load factor below a certain threshold, you want to rehash and resize the table whenever the threshold gets exceeded so that you can increase the size of the table and lower your table's load factor. And yeah, space complexity will be with respect to the table size because that's where you're putting everything in. So O of n average, O of n worst. And I'm not going to read through this entire slide, but this is also a good table to have like on hand for exams and stuff. Okay. So yeah, if you have perfect hashing, then you'd have 0 collisions. But the downfall of having perfect hashing is again the age-old struggle between time versus memory efficiency. But basically, if you wanted perfect hashing, you'd be using a lot of memory probably. Okay, so let's go through resizing and rehashing. So again, like I said, resizing hash tables, the point is to reduce the load factor. So you would basically make a new container, rehash every element in your old table to the new container, and then delete the old container. And this is only necessary when the load factor is high enough, which would maintain the amortized O1 insert. So every time the load factor is exceeded, you would make this expensive call to like make a new table so that in the next few inserts, you would maintain an O1 insert. Any questions about that? Okay, I'm gonna assume no. Okay, so how to rehash. Let's actually, well, these are the steps on how to rehash. Helpful for doing the coding portion of lab 7, but let's look at an example. So let's call this our old container, and this is our new container that we built. So we would skip the, well, basically we'd scan through the whole container. We'd skip the first element because it's empty and we don't really care about that. For the next one, we would, so this indicates that B hashes to 17. So 17 modulo modulo 8, because this is the size of the new container, is going to be 1. So we put b at 1. Yeah, so b goes to 1. And so for q, 39 modulo 7 is going to be, oh, sorry, modulo 8 is going to be 6. So we put q at 6. Oh, I skipped this. So yeah, we would skip the deleted element because we actually don't really care about that. That doesn't exist in the table anymore. So, I am bad at math. Yeah, I am. Okay, so 39 would go to 7 instead of 6. Ignore me from before. Yeah. So notice that we did not just copy the value at index 3 to go to this index 3. That's not what we're doing. We're rehashing everything based on the size of the new table. Any questions about this? Resizing and rehashing. Okay. So yeah, once we're done putting all the elements that actually exist in the old table into the new table, then we can just delete the old table. Okay, so summary about hash tables. Good time complexity, O1 average case for basic operations like insert, delete, find, and there are many uses for them, and coding interviews, love them, because it's super fast. And great when amount of data is known ahead of time. So cons, a good hash function can make lookups slow because you basically want the hash function, like the hash function might take a while to compute. Poor spatial locality, which means that similar data is distributed randomly in memory. Hash tables usually take up a lot of memory. And it's unsorted. So if you want to actually sort the keys, then you should use the ordered mapper set. All right, so I was doing a lot of talking, but let's do a practice problem before we move on to the written problem. So let's talk about this. Suppose you're given a set of n distinct words, all the same length, m, and we want to find a pair of words that are similar, meaning that you can obtain one from the other by changing just one letter. So like cart goes to cast because cart and cast are one letter apart. Cast and cost are also similar, but cart and cost are not because that's 2 letters different. So we know that n is a much bigger than m, and we can also assume that m is greater than or equal to 3, and the algorithm may use any amount of memory, and so that is all a recipe for a hash table. So can anyone say like what we might do to approach this problem? Like what would we be hashing? Like what would the key be? Okay. Yeah, let's talk about the algorithm first. Can anyone tell me what we would be hashing? Okay, for the sake of time, I'll just say that we would be hashing, we can put like a dummy letter for each letter in the in every word. So we'd have like *, art. So if we had the word cart, we'd have *, art, C *, RT, CA *, T, CAR *, and that would be what we are hashing. And so we maintain an unordered set for every string and for every letter in the string removed from that word. So we'd have like for each string for, let's call it like I equals 0 to m minus 1, because we know that all words are of length m. And we'd basically just be looking for the word with the letter and the ith indexed replaced with an asterisk. And so question about that. What would the worst possible worst case running time be in this case if we had this algorithm? And also assuming that, not assuming, because O of m, looking up a string of length m is going to be O of m. Okay, O n times m. You are super duper close, but remember that we don't have an O of 1 lookup here. We have an O of m lookup because we need to compare the strings. So if like m equals 4, like before, we'd be comparing CAT to the key CAT. So the complexity would be O of n times n squared exactly. Yes. Oh, okay. Yeah. Okay, did that make sense? Anyone have any questions about that? Wait, where did the M code come from again? Okay, so yeah, so earlier, okay, this would be like the kind of like skeleton code for the or like pseudocode for the algorithm that we have for each string. We have or for each word we have n distinct words. So that's n. This would run n times. This would run, the inner loop would run m times because we have m letters in each word. But then we also have an O of m lookup because once we, this operation of looking for a word with letter I replaced, looking for the word is also an m operation because you'd be comparing a string of length like m, so like cart to, or well, I guess to be super precise, like with an asterisk, to the key, which is CA asterisk T. And so that's length 4, that's length 4. Comparing strings is O of M operation. And we say it here. Note that it takes O of M to look up a string of length M in a hash table because it must be hashed and compared for equality. Okay, yeah. So, all right, let's do the handwritten problem. I'm going to end the recording now. Oh, I almost ended the meeting.